Okay, folks, so our next topic, as I've mentioned before, we're going to continue on with the concept of equilibrium. At this time, for this next test, we're going to apply it specifically to um, acids and bases, and then actually salts form an equilibrium process as well. But we'll take care of acids and bases first. And again, a pretty important topic, just as equilibrium was, but quite a bit extra information for equilibrium goes in to this particular topic here. So we'll just go through a few of them. First of all, the concept of not all acids are as strong, and strong as a term we'll have to define, but not all acids are as strong as others. In fact, there's only about 7 acids that are considered strong, and the rest of them would be considered weak. And you have to know that by formula, a strong versus weak acid, so you have to be able to recognize them by formula, but also why, so the theory of why they're strong or why they are weak. We're going to start calculating pHs, whether they're strong or whether they're weak, weak being a little bit more intense in terms of finding the pH, strong being a little bit easier. We're going to stay pretty heavily in the Bronsted-Lowry theory of acids and bases, and I'm going to cover all 3 theories of acids and bases pretty thoroughly, just because I think it's going to be good. I'm not sure how much we've seen of this here in the past. And then finally, you'll get a lot of multiple choice questions that are going to ask you what salts are acidic or what salts are basic, and being able to recognize those will be key to obviously solving those multiple choice problems. So what I want to do here is, this may not be a review. I know it says review at the top, but I do want to go ahead and go through the acid-base theories that we will talk about. I think I'm going to take care of 2 in this video here. The first of which is also the earliest acid-base theory that was proposed by a gentleman by the name of Arrhenius. He was the first one to really notice that acids would conduct electricity when placed in water, therefore leading him to believe that acids formed ions when they were placed in water. So what Arrhenius said an acid is that it must be able to produce a hydrogen ion when placed in solution. So just as that equation says, an acid will form 2 ions when placed in water. The hydrogen ion is always the cation, which is why we always say acids start with H. And then any of a multiple number of anions could potentially be that A- that we see right there. So just pretty basic theory in terms of acids go. And he also said that bases must be able to produce the hydroxide ion, because he also noticed that bases would conduct electricity as well. And we're a little bit more familiar with these. Obviously, OH is the hydroxide ion. B is any of a number of different cations, whether it be sodium or ammonium or potassium, calcium. We can go up and down the list here. But at the end of the day, Arrhenius said that acids produce hydrogen ions in solution and bases produce hydroxide ions in solution. And the word ionized there is pretty key, because he discovered this because these solutions conducted electricity. Now, there are a few words that we're going to use to refer to acids and bases. This hydrogen ion here, let me get my pen. This hydrogen ion is basically what we just call a proton, because hydrogen has 1 electron, but since it's positive there, it's obviously given that electron away. So the only thing left is a proton. The most common isotope of hydrogen actually doesn't even have a neutron, so a lot of times we'll call that a proton right there. So the variety of acids can have 1 hydrogen ion, like hydrochloric acid, or it can have 2, such as sulfuric acid, and then there's even some that do have 3, like phosphoric acid. At any rate, we will put terms in front of the suffix protic to tell us how many hydrogen ions that acid could donate. So in this case, only 1 hydrogen ion could be donated, so we call that a monoprotic acid. In this case, 2 could be donated, so we call that a diprotic acid. And then finally, the last one, 3 could be donated, so we call that a triprotic acid. Doesn't have anything to do with strength necessarily, and as we get further and further into this topic, we'll talk about whether or not any of those are even strong or weak acids. The term that we will use for bases would be mono, di, and tribasic. So the most common monobasic base would be sodium hydroxide. Again, just 1 hydroxide ion could be donated. A fairly common dibasic salt would be calcium hydroxide. Again, 2 hydroxides can be donated. And then a third, and I'm just kind of coming up with this off the top of my head here, this would be an example of a tribasic base, just due to the fact that there are 3 hydroxide ions. Okay, this is a good time to refer to what the term strong means. Strong does not necessarily mean that it will hurt you the worst of all acids. Weak doesn't mean that it will hurt you the least of all acids. What the term strong refers to is to what degree does the acid, or base for that matter, dissociate when placed in water. So the more that dissociates, the stronger the acid is. And what I mean by dissociate is we are going to form this hydrogen ion in water, okay, separating or dissolving, if you want to think of these like salts. Basically, acids are salts, and they dissolve in water to form these ions. So the degree to which they will dissolve, or the degree to which they're soluble, if you will, and ionize, that is a strong acid or base. And in order to call something strong, it must essentially dissociate all the time, 100% of the time, into its ions. So what we have to understand here is that the majority of the time, in fact, there's only 7 of these strong acids. The majority of the time, acids are weak, and that's because this is going to be an equilibrium process. Okay, most acid dissociation processes are equilibrium, meaning that they can go backwards and reform the undissociated substance just as easily as they can go forward and dissociate. But this is key. We have to understand that our 7 strong acids and bases, 7 strong acids that is, are not considered an equilibrium process. These reactions are said to go to completion. So for our strong acids and our strong bases, it is just a completely normal or non-equilibrium process, because the equilibrium is so high, the constant that is for these, that it won't even go back to the left. So the majority of the time, acids and bases are an equilibrium process, but our 7 strong acids and then our strong bases are not an equilibrium process at all, because the K is so high that we even get an undefined number due to our denominator being 0. Let's go ahead and list our strong acids and bases, and these folks just need to be memorized. And you can pause this obviously and write these down, but we're going to get our strong acids here, and I said that there were 7. Okay, so most of them are monoprotic acids, as we see. The only one that's not is the top one, the sulfuric acid. Now, it's important to understand that sulfuric acid is only strong when the first proton comes off. In other words, the hydrogen sulfate ion, that is a weak acid at that point. This hydrogen does not want to leave this sulfate quite as readily. So the only strong portion of sulfuric acid is when the first proton comes off. The second one is considered to be a weak acid. But as I said, these just need to be memorized, and there's no easy way or other way to go about it other than just memorizing. Our strong bases would be all of our alkali metal hydroxides, calcium, strontium, and barium hydroxide. And obviously the list is not as long here, but remember, all of our alkali metal hydroxides, so that'd be sodium hydroxide, potassium hydroxide, and then obviously on down the list. But these are the most common ones, I will say. Our alkaline earth metal hydroxides here, same situation as sulfuric acid over here, only the first hydroxide coming off is a strong base. In other words, this little complex that we have there is considered a weak base. That hydroxide ion will not come off very readily. Okay, going to get into our neutral ions. I talked about the salt early on in terms of whether a salt is acidic or basic. And this is another thing here that's pretty important, because it tends to be a question pretty often on the multiple choice portion of the test. And what we get here is just as there are 7 acids and that are strong acids, there are then 7 ions that become neutral that when are placed in water. So what I'll say is the 7 ions of the strong acids and the cations of the strong bases, those are going to be called neutral ions. In other words, salts of these substances, when placed in water, are going to have a pH of 7 or neutral 7. And everything else is going to be either an acidic ion or a basic ion. So just an example here. Here's one of our strong acids, hydrochloric acid. So the chloride ion then, if we were to place a salt of the chloride ion in water, it would be neutral, because again, the chloride ion is an anion of a strong base. So that is by rule, that is neutral. But if we were to pick another acid, this time a weak acid, this is nitrous acid, not to be confused with nitric acid. This is a weak acid. So if we were to have a salt of that nitrite ion, such as this right here, this would not be neutral. And we'll talk later about how to predict whether or not that's acidic or basic. But the idea here from this slide here is getting you to recognize ions that are either going to be neutral or not neutral. I don't want you to recognize neutral, acidic, or basic. I want you to recognize neutral or not neutral. So if it happens to be an anion of a strong acid or a cation of strong bases, those are going to be neutral. Everybody else is not neutral. If we want to do a base here, we can. Here's a strong base right here. So the cation of that strong base, the sodium, has got to be a neutral ion. Okay, so the last thing for this slide here is the last acid-base theory that I want to talk about here. This is the most important one, the one that's used most frequently in AP chemistry, and that is the Bronsted-Lowry acid-base theory. Two different gentlemen actually working separately discovered the same thing at about the same time, so rather than fighting over who to name it over, they just end up with both being on the name. So what we have is we're going to slightly revise the Arrhenius theory here and call acids proton donors and bases proton acceptors. So what I want to be very clear about here are basically the revisions that were made to the Arrhenius theory of acids and bases. And what that includes then is a revision to bases, but simply restating what Arrhenius said about acids. Arrhenius said that acids are hydrogen ion producers when placed in water. Well, that's essentially the same word as donor. So no difference in terms of acids in the Bronsted-Lowry theory versus what Arrhenius said. It's really bases that made a difference. Remember, Arrhenius said bases are hydroxide ion donors, whereas Arrhenius is going to say bases are simply these acceptors right here. They bind those in solution. So as we said, the idea of an acid remains the same, but this base is what is going to change basically. And another good thing about the Bronsted-Lowry acid-base theory is it sets up a situation where for every single acid-base reaction there has to be both an acid and a base, which wasn't necessarily true in Arrhenius' theory. But really what led him to believe this is because he knew that ammonia acted as a base. It neutralized things, it neutralized acids, but according to Arrhenius, it did not have this hydroxide ion here. So he had to have some sort of way to account for how ammonia could be a base when it does not have the hydroxide ion. Well, it turns out whenever ammonia is placed into contact with an acid, what it will do is actually it will accept the hydrogen ion from the acid and it will become the ammonium ion, and we get this anion left over. So it is accepting this hydrogen ion and bumps that number from 3 to 4 and ends up neutralizing a solution of acid, which Arrhenius could not explain. Now, the last thing I do want to talk about here before ending this video is the concept of the hydronium ion that we see show up in the Bronsted-Lowry theory of acids and bases. Water is going to be able to act as an acid or a base, and when water acts as a base, it forms this hydronium ion right here. A lot of chemists argue about whether or not acids are this hydronium ion or the hydrogen ion, and it turns out they're both the same thing. Some people like to consider the hydrogen ion as being a part of water. Some people will just as soon consider it like that, but this hydronium ion is simply an acid, and just as this represents an acid, so they're essentially the same thing, so we won't differentiate between those. I tend to use the hydronium ion more than I say the hydrogen ion, but again, that is just my preference.